Dr. Mather, thanks for joining. You are a Berkeley grad. You worked on COBE and won the Nobel Prize for that, which we'll go into. And you've done almost 30 years in the James Webb Space Telescope team as a senior scientist, and now you're working on hybrid systems as well. So we'll talk about those. I think what we can start by doing is just jump into kind of your early life and start wherever you want, but I'd be interested in hear like how you got into science for the first time.
So I hear that when I was 3 years old, I was already demonstrating my curiosity by taking the doorknobs off in the house. So parents imagined something was interesting about that. When I was 6, I still sort of remember this. My dad told me at bedtime that we are made out of tiny cells that have chromosomes in them with genetic material. And I thought, that's really interesting. We don't all get the same. This is good and bad luck for people. It immediately makes a person think about our competitive advantages, the things that we have that our neighbors do or do not have. So it's and you wonder where you are in the world. Are you going to be able to do something interesting? As it happens, I am, but you never know. So already beginning very young to think about that. I remember that in like first grade, I was already aware of the idea of infinity, and I guess you're about 6 years old in first grade. So stuff was happening already. By the time I was in third or fourth grade, I was really a beginning science nerd. I was reading books about famous scientists and starting to collect stuff and read stuff, and had my mushroom collection, which of course only lasts for a moment before they all perish, and leaf collection that dries up really fast. Stones, minerals in our area, you could pick up fossils on the ground, a few of them, in far northern New Jersey.
Yeah,
it was an area which had been run over by the glacier. So I lived on a research farm of Rutgers University because my dad was a geneticist working on dairy cows to get more milk and better milk and improve the protein content. So he was a scientist. He didn't talk much about his work, but when it came to be a ninth grade biology project, he taught me about analysis of variance for my experiment on feeding baby rats to see what they liked and did not like.
Oh, cool.
So that was I was just beginning to get an intuitive feel for things like that at that point. Childhood included riding a school bus to elementary school. Then my mother started teaching at the school, so then it was ride with her. Then riding a school bus about an hour to my high school in Newton, New Jersey. So there's another Newton besides the one in Massachusetts.
Yes, you know it. Yeah.
They're everywhere.
Yeah.
So anyway, I got interested in electronics and astronomy. We went down to see the Museum of Natural History in New York City, and heard about the possibility that there might be canals on Mars, because we didn't know yet that they were not real. Possibility of hunt for life. So pretty exciting time to be a kid. And for TV shows about wonderful science things. Bell Telephone Lab sponsored some of them. There was Ask Mr. Wizard, which was very popular on TV.
Okay.
So lots of ways to get excited about science, but sort of especially starting with a museum. The dinosaur skeletons, and to see the planetarium show, and you see the giant meteorite that sits next to the planetarium and say, how did that happen? Why are rocks falling on us from above?
Yeah.
So that immediately makes you think about the history of everything. And then volcanoes. Anyway, pretty interesting time to be alive, huh?
Yeah, I was just there. I saw the new planetarium. Have you gotten a chance to see that?
Yeah, but not lately. But yes, indeed, it's a very different one from what we had in the old days.
Yeah.
But anyway, big and beautiful.
Yep. Yeah, it's a great one. And then the canals on Mars. That was veins in the eye, right? Blood vessels.
Yeah. It seems to be the blood vessels in the back of the eye of the observer.
Yeah.
And so they'd be there every night.
Yep. Yeah. So that's funny. Okay. And then you somehow found your way to Berkeley. You got into Princeton, but you didn't want to go. Can you talk about that?
Yeah. So I was an undergraduate at Swarthmore College.
Yeah.
And I thought, well, I'm from a country high school. I don't know how I'm going to do, but it turned out I was quite well prepared because of all the things I've been reading about and thinking about and trying out at home. So, I finished up doing very well there, and then time for graduate school. Now what do? Princeton's great, but I went up to see my friends up there, and they said, we don't like it because there are no women here, and don't come unless you're married.
Right.
Oh, okay. Well, I had a summer job lined up in Berkeley anyway.
Nice.
Because of another friend that I had and from high school. He was out there, and he sent a picture of himself sitting on the fountain in January in a short sleeved shirt. Come on out. He says, okay, I'll try this. So this is sort of an example of how my life has gone. Somebody says, you want to try this? And I say, yes. And then it turns out.
Yeah.
It doesn't always, but that one did. So I'm at Berkeley, and I think the coolest thing is I want to be a theoretical physicist because Richard Feynman was so cool. That's what I thought.
Yeah.
Turned out he wasn't so cool in every way, but anyway, he was a great scientist, and I want to do that. So I asked my faculty advisors, what do I do now? And they said, are you wealthy? There are no jobs in that territory. Oh, no. So then I go around and ask physics faculty, well, what you got to do that's interesting? And so, okay, it's not going to be theoretical quantum mechanics. It's going to be, let's try to measure the cosmic microwave background radiation, which had just been discovered a few years before that. And so, okay, well, it's possible for a graduate student project to make some progress. So we started I was working with Mike Werner, who you might have also heard of because he ended up as the project scientist for the Spitzer Space Telescope, which was a pioneering infrared mission. And so a friend of mine and a great scientist. Anyway, we worked together for a bit. Then my thesis advisor was Paul Richards, and he's went off to Britain and came back with an idea for a balloon payload. Basically, we'll set up a spectrometer on this balloon payload and see if you can measure the cosmic microwave background radiation from above most of the Earth's atmosphere.
Right.
So, okay, so we did that. We built it. There were several of us, Paul and a couple of other graduate students, David Woody in particular. And so we built it, and we went down to Texas to launch it. I actually drove a big university truck with David Woody through all the way from Berkeley to Palestine, Texas.
Wow.
And so we launched the payload, and it went up, and it did not work.
Yeah.
Oh my gosh, it does not work.
Right.
So what do I do now? Well, my thesis advisor said, well, you did good work. You also, the thing you did with Mike Werner was good. It proves you can do stuff. Write it up. So I wrote it up, and I thought, well, this is way too hard. I'm never going to do that stuff anymore. And I got a job. I'd gotten a job offer for NASA in New York City. Going to be a radio astronomer. Going to learn something else. Okay, cool. And then I've been there about 6 months, and NASA said, anybody got ideas for a new science mission? It's satellite projects. Because the Apollo program was winding down. What are we going to do now?
Right.
Yeah, my thesis project failed, but we should try it in outer space because it would be better. The whole point was to be above the Earth's atmosphere, and space is above the Earth's atmosphere.
Yeah.
Okay. So my boss said, my postdoctoral advisor said, okay, yeah, I know. That's right. We should try this. We'll call up our friends. We wrote a thin proposal, and it had the basic idea of the whole mission that we eventually flew 15 years later.
Yeah, it was the ancestor of COBE in many ways.
Within a few weeks, we had the general idea.
Yeah.
Of course, we didn't know the specifics, but we had chosen the orbit that we wanted, and we'd chosen the design. We knew we had to spin the spacecraft around. So that thing that we eventually flew was not far from what I drew for the proposal.
Yeah, and can you talk a little bit about why? So you had something on the surface as well as the balloon. Can you talk about why you had two and kind of the hybrid approach, why it's important?
Well, in those days, people did measurements from the ground because at some wavelengths you can see quite well from the ground. But at the shorter wavelengths, the Earth's atmosphere is pretty opaque and has lots of emission of itself. It's shining down on us because there are molecules up there doing things. So definitely that's why you have to get the best equipment will have to be above the Earth's atmosphere. So we knew that we needed to do a measurement above the Earth's atmosphere to see how bright is this cosmic radiation at every wavelength.
Mhm.
As the key prediction of the expanding universe story is that it should be what we call a perfect black body spectrum. It is a formula worked out by Planck in the late 19th century.
Mhm.
And basically it says an ideal radiator will produce this shape of spectrum, the right amount of energy at each different wavelengths. So, okay.
2.725 Kelvin? Yeah.
That's the number we got.
Yep.
So how are you going to do it? Well, the idea that I put forward and which people liked was, okay, well, put up an apparatus that measures a spectrum and also put in a calibrator, an ideal piece of plastic that radiates just exactly the way that the universe would if it were according to the prediction.
And this was the XCal, right? Basically.
The XCal, it's the external calibrator. Yep. So build an apparatus which basically makes a differential comparison. Here's the sky, here's the ideal, do they match?
Mm-hmm.
So that was the story, and eventually we've got to fly it, and it was actually the first thing that got us a result. Within weeks of launch, we knew the answer was yes, it's perfect.
Yeah. Well, so we're going to talk about this. This is hugely important, but getting selected among hundreds of.
Yeah. How did we? Well, okay. So I'll tell you a little bit more about that part.
Yeah.
When our little team of 7 people wrote our proposal, we had us at NASA, a couple of guys at MIT, including Rainer Weiss.
Okay.
And David Wilkinson at Princeton. And so we wrote our little proposal and we thought, what'll happen? And it's a good idea, but competition stuff. We didn't know at the time that we wrote it that 2 more teams were proposing related experiments, one from Berkeley and one from Jet Propulsion Lab.
Wow.
So a couple of years later, NASA said, yeah, we like these ideas. What we want to do is choose members of these 3 teams and make a new team of scientists. And we want you to work with the engineering team at NASA Goddard Space Flight Center here in Greenbelt, Maryland, where I am still today.
Mm-hmm.
So that's what we did.
Yeah.
So we started drawing and sketching and talking to engineers, the really good engineers that had just finished flying the International Ultraviolet Explorer, which was a remarkable telescope. It's a small diameter, but a huge result because it was able to see ultraviolet light. And you could sit here in the basement of Building 21 at Goddard and drive it.
Right.
And so I pointed at your favorite target, make sure it was working, doing the thing you said you wanted it to do. And anyway, so this team was able to sketch out what we needed to build and how we were going to do it. So got started with a very serious team, and they got it right. Of course, there were a few steps along the way, like challenges. Like we said we're going to go up on a Delta rocket. That's the right answer. Then a few years later, NASA, in its great wisdom or not, decided they would fly the space shuttle. And to get the funds from Congress to fly the space shuttle, they had to agree to give up all of the expendable launch vehicles. Okay. Which turned out to be not such a great idea when the space shuttle blew up.
Yeah.
Challenger. And so our design, which we had made to be compatible with the Challenger and other shuttles, was not ever going to fly. So now what do? Have to redesign and go back to an expendable vehicle, a Delta launch rocket. And there weren't any. But as it happens, there were enough spare parts lying around the world in warehouses that you could assemble one.
Oh, wow.
So that was pretty exciting. So, and it turned out that, and this is not something we would have ever expected or planned in advance, we were in a position to be the first scientific mission to be launched after the Challenger.
Okay.
So we did. Then the first space shuttle after that was the one that carried the Hubble into orbit.
Wow.
So it was very exciting times and tough times because responding to disaster.
Yeah, a lot of weight on this one. And let's talk about the Ferris, kind of how it was, because that was your instrument, and it was made tuned perfectly. The interferometer was a little more sensitive to the wavelengths needed to see what we wanted to see, right? And then of course the genius of having the actual trying to get a null up there or a diff up there instead of getting the actual feedback back that might be tainted in some way. So can you talk about maybe the more technical aspects of it, which is super interesting?
Yeah. Well, of course, as we already said, the fundamental idea is a direct comparison of the sky radiation with something that radiates the way we say the sky ought to be if it's the Big Bang is the right story.
Yep.
So, but to back up to how does the spectrometer work?
Yeah.
It's an interferometer. So the way that works is the light comes in from the sky, and we focus it into a beam, and then we divide it into two equal parts.
Mm-hmm.
And then we send one slightly farther than the other, and then bring them back together and make these two waves interfere. And so now we have something called an interferometer, and when you change the amount of delay in one of the arms, then you change how the interference works. So this is a way of encoding the wavelength of the light that you're getting into the pattern. So instead of a curve that shows how bright the light is at each wavelength, you get what we call the Fourier transform. How the brightness depending on what's the spacing and the delay in the two waves. So, but they're equivalent information. If you take the interferogram curve and make a Fourier transform of it, you get the spectrum back.
Yep.
So that was the innovation that came from Paul Richards, who got it visiting Britain years before us. And
they were wire grid polarizers, right?
Yeah. So how are you going to divide a millimeter wave beam into two equal parts?
Right.
This is tricky. So the classic interferometers used a thin sheet of plastic to divide something into two equal parts, but that wasn't going to work because the plastic you needed was the wrong thickness at some wavelength. So, and it wasn't that transparent either. So try something else. Use the polarizing system. So, if light hits a polarizer, some of the light will go through and some might bounce back. So the idea is divided equally with polarizers, and then very carefully manage the polarization. So when it comes back, it still interferes.
Yeah.
So that was something other people had invented. Guys in Britain named Martin and Poplet had done that part.
Yep.
So thanks to an ongoing series of inventions other people had made, we were able to say, yeah, we'll do it like that.
Yep, and it works. It was 50 parts per million, I think is
yeah. In the end, we had to. First, what you start off with is many thousands of these curves of the interference pattern, and then you have to say, well, what does that mean, and how many mistakes have I made?
Yeah.
So, of course, there's always some kind of interference bothering you. So Dale Fixon was the wizard who said, I know how to figure that all out. I'm going to make what we call a least squares fit. And I've had an idea of what each bad thing would be and how it would affect the patterns.
Wow.
And I'll look and I'll recognize those patterns and I'll subtract all that out. And what's left will be real. And so that's how we got to the 50 parts per million.
Yeah.
Because we didn't talk about one of the hard problems, which has turned out to be a very useful problem for other people. Cosmic rays hit our detectors. So cosmic ray, just a charged particle coming through space, splat hits our detector, goes through or stops in it, and gives a blast of energy. Suddenly raises the temperature of the detector. Well, the thing we were using to detect the infrared radiation is the temperature of that detector. So here we're measuring this nice little wiggly curve with an interferogram, and then, flip, there's a jump on the temperature, and you have to say, I don't like that. Got to remove all of those too.
Right.
It makes this a much more interesting job than a thing you could do in your lab.
Yeah, and that brings up the whole thing of the cooling itself. It was super hyperliquid helium.
Yeah. It had to operate at a very low temperature.
Yeah.
The detectors run at about 1.5 Kelvin.
Yeah.
Which is below the temperature of superfluid liquid helium. So this is how we're going to get something really cold in outer space. Have a tank of helium down to very low temperature, which is another something that somebody else had invented and we could use.
Yep.
We should talk about helium for a moment here.
Yeah.
How are you going to get something really cold in outer space? Well, get helium. So helium is pretty abundant in the universe, but it's hard to get here because we don't. It's not. Well, our source actually is radioactivity in the rocks in the Earth. So when you want helium, you have to go to a place where you can get that, and it comes up from natural gas wells. Anyway, so somebody has to go get helium that way, and we compress it, liquefy it with a giant refrigerator until you can get it extremely cold.
Yep.
Then you pour it into your tank, which you're going to send up into outer space. And now you have your interesting challenges. How are you going to keep it from getting out?
Yeah.
So helium has an astonishing property called superfluid. If it gets to a temperature below 2.18 Kelvin, it transitions into a quantum mechanical state of superfluidity and has zero viscosity.
Oh, wow.
Oh my golly, that's why it's called a superfluid.
Yeah.
And because of that, there's also a special quantum mechanical effect that you can use to keep it in the tank and let it evaporate just as much as you want it to do.
Huh.
We put up a porous plug, a little bit of ceramic, and there's a temperature gradient across the porous plug, and the helium passes through the porous plug and vaporizes on the outside. Meanwhile, cooling the outside produces enough pressure gradient to keep the rest of the helium in.
Wow.
So this is something that was discovered a really long time ago and
very useful,
perfected by other people who wanted to use it and did use it to measure to test Einstein's general relativity with a satellite that was called the GPB. They built it at Stanford. So that was a long time ago that somebody invented it and we used it. So this is another story. Well, we pulled the ideas together and made something that hadn't been done before, but we needed everybody else's inventions first.
Totally. Yeah. And that's the case with almost everything.
Yeah, it's always the case.
It's a beautiful thing. Yeah. Because I mean, and your stuff that you found will be used, I'm sure, for the next generation.
Yeah. So what we did is now superseded by many other things. Anyway, having this super cold thing was what, and the perfect black body, almost perfect.
Yep.
That was what enabled us to get the 50 parts per million comparison.
Yeah.
To the predicted spectrum.
Yeah. And that cold, the instrument that kept it cold also kind of gave it a predictable life, which is kind of sad. Of I think 10 months is the usefulness.
When liquid helium's all gone, you're done.
Yeah, you're done. You're done. So
I want to say a couple of words about what's next in this territory because
sure.
Our answer was so perfect that people pretty much stopped thinking about it or trying any harder. After you say something's perfect, what do you do?
Right.
Hardly anybody has to write a paper about it anymore until you think of something that makes it imperfect.
Yeah.
So there are a few papers that predict, if you could have a much better experiment, then you could measure the imperfections that would be caused by processes that happen when the universe does its decoupling, when the universe cools down through the transition where all the electrons latch onto atomic nuclei and suddenly the sky becomes transparent. As early universe becomes transparent. So details of that structure could be dissected in variations from this perfection. So we actually have a project in mind here at Goddard called PIXIE. And Al Corbett was the guy who been leading that project for quite a while. We figured out how you could actually measure it about 10,000 times better.
Wow.
So it's basically the same idea, only better in so many ways. But right now we're not doing it. It's expensive and nobody says we have to do it.
Right.
But when somebody says, I predict this from string theory or some darn thing that comes along, and if you build this apparatus we can test.
Yep.
And then maybe we'll get to fly it.
Yeah, we just got to wait for the theorizers to do their thing.
We need a sufficiently strong push to please measure this for us.
Yeah.
To justify that much effort. But
yeah,
we can do it.
Yeah.
We should talk about the second thing that made this brilliant discovery, though, that Steve was
spottage.
So the early universe is spotty or lumpy.
Right.
And we sort of thought it must be, but nobody knew.
Yeah.
And why would we think it must be? Because there are galaxies. And if the universe had been perfectly uniform, as it started to expand, we calculated it would never turn into galaxies.
Yep.
It had to have some kind of primordial seeds, something that said, well, it's just a little bit more gravity over here. It's able enough to stop the expansion. So it was predicted that we had to have something. But when we started off the mission with our proposal in 1974, there was no serious understanding of that. By the time we launched, there was a pretty good prediction, or a few, and some people got about the right answer, which is gratifying, but they probably wouldn't have bothered to try to calculate if nobody could measure. But they knew we were about to measure, so it makes it worthwhile calculating something that's really pioneering and different. So anyway, so what's that experiment? That's called the differential microwave radiometers. And 3 different versions were included in our original 3 teams. So we had to decide exactly which one we were going to fly. But basically, it's another differential device where you compare 2 directions in the sky. We point 2 antennas 60 degrees apart on the sky. And say, well, are they giving the same answer? And then we rotate the observatory and make measurements of all possible combinations of 2.60 degrees apart on the sky. So have millions and millions and millions of measurements of these 2-point differences. And then again, through the magic of least squares fitting, we say, here's a model of the sky. It's got 6,144 pixels on it. And please make a map that fits the 100 million measurements that you made as well as possible. So that's the scheme, and it was pretty tricky. Number one, the signal we were hunting for was very small. And number 2, there were lots of kinds of interference we had to worry about. And so you couldn't just look at it and say, well, that's perfect, because you're looking at something that's almost undetectable. So the story on that one was we build it, we launch it, we know right away that it's got a problem. And the new problem we knew about even before we launched is magnetic field sensitivity. The device we had to use was sensitive to the presence of the Earth's magnetic field. And so, well, we think we understand this. We knew that was going to happen. Now make a model of that, subtract that out, and then are you sure? So, and then there were other things like a little bit of light from the Earth will bend over the edge of the sunshade and shine into the apparatus. And we should detect that a little bit. So make a model of that, subtract all of that. Then the third thing that we had to take care of was the galaxy. We live in the galaxy, the Milky Way galaxy, and it's full of electrons and dust grains. And those are emitting at wavelengths around the same wavelengths we care about, in a few millimeters. So make a map of that and subtract that. And so do the best you can. So when you start off, you see this, in our picture, a bright red band across the middle of the map. That's where the Milky Way is. And when you're done, you say, I don't see the Milky Way anymore. We probably fixed it. So that's a multi-step process to get something you think you believe. And hugely difficult. So after we saw the first data with the maps with the blobs in them. And it was produced by Ned Wright, one of our science team members. He did it by himself with his own computer program. And he was basically right. And we said, but Ned, we can't just use your answer. We have to be sure. So we did the thing over again, multiple different ways, looking for all these different errors that I was telling you about.
Yeah.
And so it took us about 6 months after that before we were able to go public and say, yeah, here's our pink and blue blobs map, and we're really sure.
And it illustrates dark energy and dark matter in a staggering way as well, which is probably frustrating to you, but also, well, it's frustrating to me, but to you, I don't know if you care as much because you're doing a precise science here, and that's just another attribute, whether you know what it is or not. I guess it doesn't matter to you, just as long as we can measure it.
Yeah, we started off, my perspective was, though I wanted to be a theoretical physicist, I'm an instrument builder now.
Yeah,
and a theoretical one at that, as I talk to other people who actually build stuff.
Right.
So our job is to make sure the answer we got is correct.
Yeah.
So at the time, there was already suspicion of dark energy. And people had published papers about why it should be there.
Yeah. To what extent was that suspicion?
Well, it's a little subtle. When you look at the pink and blue blobs map that we made, it's not that obvious which ones have the effect of dark matter or dark energy in them or not. Yeah. So that became much more clear when we got the successor missions, the WMAP and Planck missions.
Yeah.
But we knew for sure that the pattern of blobs would be affected by these features of the universe. And basically, how many large diameter ones are there compared to small diameter ones? And that is affected by two things. One, the presence of the dark matter, which much more gravity than ordinary matter, and the rate of expansion, which changes the schedule of everything. So it's now possible with modern measurements to say we have measured the effects of dark matter and dark energy on these blobs with a precision of a few percent. It's pretty astonishing to me. When we first saw the blobs, we did not know any of that was going to happen. We were hopeful that it would be important, but from us, our job was, let's just measure and be really, really sure.
Right. After the Nobel, you transitioned into James Webb. How far after COBE did you do that?
Well, pretty quickly.
Okay.
So we ran the COBE until 1994.
Okay, that's when I was born.
So we finally said we're not getting much more data about the background radiation anymore.
Yeah.
And so turn it off, but keep on calculating and making those maps better. Yep. So I'm just thinking, well, what do I do now? Maybe I should go to a university, build a program, start some other idea.
Okay.
I started thinking about a telescope in space that would unfold, because we knew we were building the Spitzer Space Telescope, and my friend Harvey Moseley said, we know it's going to be good, but it's not big enough. There's going to be so much science you could do with a bigger telescope. Okay, so I started drawing sketches about telescopes that unfold. And a few months later, I get this phone message from NASA headquarters. Well, we're going to start studying this new telescope. It's called, we didn't have a name yet. Would you like to work on it? And if you do, call up this guy and send me a proposal for it tomorrow.
Tomorrow, yeah. Right.
So it means that other people knew and had been working on this quite seriously, and they knew they needed a big telescope in space for the next big NASA mission.
Yeah.
And I had been just keeping my head down for a while, not thinking about other things. So I said, of course, I'll do that. It's the coolest thing I've ever heard of.
Right.
So I just dropped every other things I could have been doing, including working on the WMAP, which we did build, but they didn't need yet another scientist. And so, yeah, I'll work on this one. So start talking to engineers and other scientists about what to do. So that's how that one got started. It wasn't originally my idea, but I was very enthusiastic when I got a chance to say, that's what I want to do.
Yeah, and what was your kind of role in as it began and as it obviously went on for the almost 30 years? Because I know there's a bunch of things that, which is a beautiful thing as well, like we didn't invent a certain amount of things yet, but that we put that into the blueprints of what was needed. So was your kind of role stewarding those things and making sure the science is being done for those?
Yeah. So at the very beginning, it's blank sheet of paper almost.
Right,
So,
right.
a few scientists, a few engineers, a few engineer managers sit together and we say, "Oh well, how about if it were like this?" And and we sit with a whiteboard and draw stuff. Well, it's probably got to be like this, and it's probably got to be like that, and it shouldn't be near Earth because it needs to be cold. And if it's near Earth, we can never get it cold enough.
Yeah.
Why does it have to be cold? Because the science says we need a really much longer wavelength. We need to study longer wavelengths because that's where the new discoveries will be. We already did what you can do with a Hubble, and it does have certain capabilities. And the next great advance will be with an infrared telescope and see things that the Hubble cannot see. So it's not going to really, if you can do the infrared that nobody else has ever done, then you're going to be thrilled with the discoveries because they're all new.
And this is because through infrared, you don't need to account for dust and all this just crazy stuff in space. Infrared can get through all that kind of.
So there's basically several reasons. One is you can't do it from here because Earth's atmosphere glows and is opaque.
Yep.
Number two, you can study cold things that are not warm enough to send out their visible light. Stars that are not quite warm enough.
Yep.
Next one is you can see through dust clouds because typically dust absorbs short wavelengths better.
Yep.
And I guess, and then cosmologically, we really need the infrared to see the most distant objects that are running away from us so fast. We get the cosmic redshift from the expanding universe. And so if you want to see the first galaxies that grew, which we see as you're looking back in time by looking at far away, you're going to have to pick up infrared light to do what you would, to see the original ultraviolet light.
Yeah.
So,
and let's talk about redshift for a second, because it's an important thing, and we're very lucky that it exists. Because if it does not exist, I don't think we know the age of anything, unless I'm wrong. But so the expansion of the universe is actually pulling the red light wave apart, and that basically tells us the age of it, because we know that that's constant. So if we can see how large that wavelength is, we can know how long it's been in space getting pulled apart. That's redshift.
That's the sort of longer version of the original story, which Edwin Hubble drew us. In 1929, he drew us the first graph.
Right.
The graph shows different galaxies, about 30 of them, I guess. Each little dot shows the velocity of motion away from us, as determined from this wavelength change, versus the distance. And you see a trend. Almost all the galaxies are going away from us, and the farther away, the faster.
Right.
Divide the distance by the speed, you get the age of the universe. It's pretty simple.
Yeah.
Now, his data were wrong about the distance. So we got the wrong age, which was a puzzle for a long time. But when we finally found out the right answer, to tell the truth, they were still arguing about the right age.
Yeah, we are. Yeah.
The expansion rate is still hard to be sure of. But anyway, so now we're pretty sure.
Yeah. Yeah.
So anyway, that's how I got started into the Webb telescope work.
Yep.
And so what did I do? Well, the first stuff is, as we say, conceptual.
Yeah.
What kind of telescope? Where is it going to be? And then we start to draw sketches, and we say, okay, well, how can we get one of those? So, okay, well, we're smart people. We're going to draw it and build it. And we went off and we had a meeting, and we presented our story to university people and aerospace contractors. And they came back after a little while and said, you all go away for a while. We've got a discussion. We want to tell you something different. They said, we aerospace industry, we want a chance to compete for your work. This is our job. We build telescopes for a living. So we want to be a participant as corporate entities. We want to build telescopes for you. So, but of course, we can't just say me. We have to set it up as a competition. So we did. We did what they told us to do. Set up competitions. We said, okay, you and you, send us proposals about how you would do this and get your teams together.
Yeah.
And we chose in the end a couple of different teams, and we say we're going to send you both a lot of money for a long time to show that you know what you're talking about, and have a basic design that we think could work. And so we did that for several years. I don't remember how many, but maybe 4 or 5 years of that.
Yeah.
And then we finally chose them and said, okay, you. So the company was called TRW, and then they got bought up by Northrop Grumman, big aerospace company, now headquarters in LA area. So they got chosen, and by the way, they said, when we were choosing them, they said, by the way, we've already unfolded 2,000 things in space, and they've all worked. That's pretty interesting, because our design requires unfolding things in space.
Right. Yeah.
So it's pretty terrifying for people who have never done it.
Yeah.
That how could they possibly? And so it's a little bit reassuring when somebody says, well, they did it before.
That's nice. Gotcha.
Yeah. So that's how we ended up with the particular design that we have. There are lots of other designs that we could have had. The other company was Lockheed Martin, and they had a completely different shape.
Oh, really?
To it. It would. I think it could also have worked. But anyway, we chose one.
Gotcha. And then what were the things that didn't exist in the design, but we needed? I think there was a cooling mechanism. There was a...
We had a list of 10 technologies that we knew we had to finish before we could even build a design around them.
Yeah.
So, okay, how do you do this? Well, number one, the obvious one is, how do you get the mirrors?
Right.
Because nobody had ever made a giant mirror like that out of pieces. So number two, the detectors. Nobody had ever made such good infrared detectors before. Number three, how are you going to focus it? Because we launched the Hubble out of focus, and that was the first question people asked us: how are you going to do that so you don't make that mistake again? So an algorithm, a method is required. We're going to need some unfolding sunshade, is a huge umbrella, and it's as big as a singles tennis court, and it ends up in 5 layers of plastic. Well, it sounds easy, but it isn't, because it's got to be just perfectly controlled. You can't just have a big piece of plastic.
Right.
It's got to be folded up, not wrinkled, not torn, and it's got to survive launch.
Yeah, that's the hardest thing.
We had we needed to find a way to cool the all of the instruments have to be cold, but one of them has to be colder. So the mid-infrared instrument has to run at 7 Kelvin.
Oh.
So that's not liquid helium.
Yeah.
You can't get it by radiative cooling. The rest of the telescope is cooled by just radiating its heat to outer space behind the umbrella. That instrument has to have a cooler, an active cooler. So it's a version of what we would have in the kitchen, where you compress a gas and it passes through the pipes and it expands at the other end and it absorbs heat and comes back. So we use helium for the gas in this case. That turned out to be pretty tricky, but we had to have it. So those are tricky things. We even needed something that nobody had done before, which is to say, we needed basically an amplifier and computer chip to go next to the detectors, but operate at 40 Kelvin. So a special, it's called an ASIC, an application-specific integrated circuit, and it runs the detectors. It sends the right voltages to the detectors, and it sends out bits to the computer. So we had to build that. Nobody had ever done that one for a low temperature detector like that. So people knew they had a version that would work at room temperature, but nobody had ever done it this well cold. So
yeah,
that's an example of what some of the things are that we had to invent.
And all the engineering needs to be done with the assumption of those temperatures, which is a whole nother thing as well.
So you draw your big design, you say, this is all the things I need.
Yeah.
Then you say, but I don't know how to get them. So you spend quite a few years proving you can get them. And you finally have people say, I can build that for you. Then you say, now we can make the design that uses these ideas and then make a coherent thing that's going to work in the end. Something we didn't fully appreciate at the beginning was how hard it was going to be to prove that it would work. So,
Right. Yeah, I guess that makes sense. I didn't even think about that.
So obviously you're not going to bet the future of the nation's science program on something where you don't know if it's going to work or not.
Right.
So we had to invent basically a version of the classic optics test that you could do when the telescope is cold in a giant vacuum tank. And the classic test says, I want to produce a collimated light beam to simulate starlight coming in. But there's no way to get one of those in the vacuum tank. So we had to find a way around that. And then we had to prove we were going to be able to focus this telescope in space somehow. So all of those 18 mirror segments that you see in the beautiful pictures, they all have each one has 7 motors on it to change the curvature and the orientation and position. Yeah. So my goodness, that's a lot of rehearsing. So we have to have a complete simulation, an algorithm that does the right thing and starts with blurry images and says, send these commands to the motors, it'll work. So we worked that all out mathematically.
Yep.
And then we worked it out by test at room temperature. And then we had to prove that it worked when it was cold.
Right.
So that was the dramatic test in Texas. We did that in Houston at the giant vacuum tank, which the Apollo astronauts used to walk down a ladder to practice landing on the moon.
Wow.
So historic facility.
Yeah.
So that was pretty exciting, and we got a little extra excitement because Hurricane Harvey poured 40 inches of rain on the outside of the building at the same time that we were doing this inside, and interrupted the supply of all kinds of things, including liquid nitrogen, which was critically important. We couldn't run out. So the National Guard had to help bringing liquid nitrogen through the storm to the vacuum tank.
Wow.
That's a big deal.
Yeah.
Our people were heroic.
Yeah.
And
so many people, so much time and effort, and it worked. And it's so
they were so conscientious, and they caught the mistakes that people might have made, and of course nothing's ever perfect the first time. So you say, I'm worried about this and I'm worried about that. So you spend months analyzing what you saw to say, is it really going to be okay when you launch? So that was pretty dramatic. But the upshot was all the instruments were working. And we know how to focus the telescope.
Yeah. So, and the process to get there also is valuable because its predecessor, which I'm sure we can talk about maybe at the end, or what that might be. That now we know how to work with industry better and do all these things that we haven't done before. So it compounds, which is great.
It certainly does, and. People like to talk about new technologies, but I like to emphasize that it's the people know how to do stuff that are really special. You can read a book about something, but that's not the same as being able to do it yourself.
Yeah.
So we raise up and train generations of people who are courageous enough and capable enough to say, I can do that for you, and actually do it.
Yeah. Congress almost shut it down multiple times. Maybe you can talk about one of those memories, funding-wise.
There was a time when it became obvious that our plan was incorrect. We did not have enough money or time to finish the plan. And so this got to be pretty embarrassing for people like Senator Mikulski, who was a strong backer of science and a great lover of NASA and the things that had been discovered by NASA. So it's pretty embarrassing. So she sent us a letter. Please send us a plan that we can believe. I'm paraphrasing, obviously.
Right.
And also, please make sure we can believe it. Get yourself some outside reviewers who say, make sure we get a detailed look at the plan and see if there's any other way you could ever do this. So we got 2 reports back, and the answer from these committees was, yeah, they did good work, and they did not ask for enough money and time. So that was enough to justify Senator Mikulski and her friends there in Congress saying, yeah, we think this is worth it. We think we can do this. Give them this amount of money and it'll be enough. And it pretty much was. A little bit of extra added trouble due to COVID.
Yeah.
But we still managed to do it within the budget that they'd sent.
Yep.
Which I think our team can be extremely proud, and especially our project managers who held it together and made people able to work together through very stressful times.
Yeah, the end there seemed unsure, especially with COVID. And then, of course, launched 2021, Christmas, pictures, everyone's happy. Seems I don't think there was any issue. There might have been a small issue if I remember correctly, but it was rectified. But yeah, it was a huge day, and
yeah, basically nothing went wrong.
okay.
We had a lovely surprise that the solar panels popped out sooner than expected.
Okay, I mean, that was
They were pushed away so gently from the rocket that they automatically deployed sooner than we thought they would.
okay.
It was a surprise, but it was a nice surprise.
Fine, yeah.
We had a lovely surprise that the rocket put us in exactly the right place, so that we have a lot more mission lifetime than we thought we might have.
Oh, good.
So those are both pretty cool. We did have a negative surprise you heard of, where we got a micrometeorite ping on the mirror.
Yes, that the bottom left little bubble there.
Yeah, the little dent.
Yeah.
And so
Sand grain.
really was are there going to be a lot more like that? And we've never had another one that big.
Right.
So we've been fortunate.
Yeah. So now let's talk about kind of the science it's doing now and the science it's going to do in the future and exoplanets and all that fun stuff. Let's jump right.
Well, we had 4 giant categories of things we wanted to do. One is, what's the first thing that happened after the Big Bang?
Mm-hmm.
How did the galaxies grow?
Yep.
How are stars born? And how about those planets out there? And so we've had wonderful discoveries in all of them.
Mm-hmm.
Our hope in the early universe story was we'll discover something that we never expected. And we have. They're called little red dots, which is a name that I gave them, and he seemed to stick.
Mm-hmm.
And literally true. They're little red dots on the picture. They're very, very compact. They're about 1% of the size of the Milky Way.
Mm-hmm.
They're very bright. They spin very fast, like 3,000 kilometers a second, which is 15 times faster than the Milky Way is spinning. Where we are. So it's a new category of object. And the hint is, this is showing that the first generation of stars were supermassive, like tens of thousands of times the mass of the sun.
Okay.
And that they could turn immediately into black holes.
Right. Immediately. Okay. Interesting.
Each one would last maybe 2 or 3 million years. Maybe it's something else going on in there, but that's a hot topic for today. What are those little red dots?
Right.
Black holes, supermassive stars are both. And how come we don't see the works? We don't see the stars. We don't see the black hole. We only see the net result on the outside. So it's as though whatever's in there has got a blanket over it, or a cocoon, as other people call it.
Right.
So it's hiding, and so we cannot see the X-rays or the radio signals or other things that would usually come out from such an astonishing idea.
Do you have a thought?
Yeah, I think it's probably supermassive stars and black holes.
Okay.
Probably not just one black hole, but a lot of them.
Okay. Wow.
So are we ever going to be able to know what's the right answer? Probably yes, I think so.
Mm-hmm.
We will find either a reasoning or a new bit of evidence. By the way, there's evidence from the chemical composition of these early galaxies that some of them have a lot more nitrogen in them than would be natural if they were from ordinary stars. And these supermassive stars are predicted to have extra nitrogen in the product when they blow up.
Right.
So there's a story we're beginning to tell, and so I think that's one of the coolest things.
Yeah, it is the new. I mean, it's a new mystery, and so I mean, I didn't even know of the little red dots. I don't think so. It's exciting.
Yeah.
How long? What's the life cycle of the James Webb? Like, what's our time limit here?
Oh, we have probably 20 years of fuel left.
Okay.
And so far, things are not wearing out very fast, if at all.
Okay. Good.
So we expect a good long run with this equipment.
Yeah.
And fortunately, our budget has been protected enough, even through the terrifying events of the last few months.
Right. Good. So we put it out in the Lagrange point. I think it's the Lagrange point 2.
Yeah.
Can we touch briefly on what a Lagrange point is and why it's important?
Yeah. So Lagrange points are places where the combined force of the sun, in this case, and the Earth are able to pull the object around the sun once a year. So the object could, in principle, stay there with no extra forces. So the Lagrange point 2 is about 1 million miles farther from the sun than we are, and moves around the sun with us. So if you put a payload out there, you can keep it there, and it won't. And there doesn't no additional force is required to keep it there.
Yeah.
So it's overhead at midnight from our perspective.
Mm-hmm.
And it's pretty close by as things in the solar system are concerned, because it's only 1 million miles away, and the sun is 93 million.
Mm-hmm.
So it's really close. It only takes 5 seconds to send a signal up, and 5 more seconds to get the answer back. So it's pretty close by.
Yeah.
And for us, the particular advantage is not that it's nearby, but that you can put an umbrella, and the telescope will not receive any heat or light from the sun, the Earth, or the moon. So it's dark. The telescope will be in the dark.
Right.
And it's only place quite like that. So go there. Now, you don't actually want to be at the Lagrange point, because it happens to be also the end of the shadow of the Earth.
Mm.
So it's dark there.
Yeah.
So we need solar power to run the observatory.
Right.
And it's easier to get cold than it is to get sunshine.
Yeah.
So, so do not go there. We're actually several 100,000 miles away from that spot. And that's fine.
Okay. So it's more of like an area.
It's an area.
Yeah. Got it. I didn't know that. Okay. And so let's now talk about one of my favorite parts of this whole thing is the exoplanets and
okay.
beautiful spectra. And I'd love to kind of talk about transit spectroscopy, which very high level is we're putting a star in between the planet, or we're putting a planet in between their kind of home star. Starlight's going through the planet and giving us spectroscopy of that light, canceling out the elements in the planet, and we can get a kind of a diff there to understand what the elements are, which is another amazing thing that we have in our science tool belt to understand, like, is this a potential Earth?
Yeah. So anyway, what you said is a good summary of that. Is once in a while a planet will go in front of the star, and if it does it over and over again, you can say, I know how long it takes to go around, and I know enough about the star to say, in that case, I know I can calculate the temperature of the planet more or less, because I know how bright the star is, and I know the geometry.
True. Yeah.
And I can calculate how big the planet is because of how much of the starlight it's blocking. So two basic things: how big and how hot. Let me say, sometimes some of the light from the planet will go from the star will go through the atmosphere of the planet on its way to our telescope, and spread out that light into a spectrum. And so an atmosphere will absorb more light at some wavelengths than others, depending on what's in it. Could have clouds, could have dust grains, could have molecules of various kinds, and each one will affect the signal differently. So now we've got a pretty large catalog of observations now, because this is very interesting, and there are a lot of planets to do this way.
Yeah.
So clearly the easy ones are the big ones. The ones that are like Jupiter and Saturn in that size range. And so we've studied them a lot. Now, here's the disappointment for a lot of people. This technique cannot work for very small planets like Earth around big stars like the sun.
Okay.
The Earth is tiny by comparison to the sun. The sun's 1,000,000 miles across about, and the Earth is like 8,000. So
Too bright. Yeah.
so you can hardly tell. The total brightness of the star will hardly blink at all when the Earth-sized planet goes in front of it.
Right.
And it works a little better if the stars are small. But then we have a different problem. That small stars mean that the planet's really in close to them, and these little stars are hostile in our humanoid version interpretation. They send out blasts of material quite frequently, which will potentially strip away the atmosphere of a planet.
Oh, okay.
In fact, the sun does this too, and it may be the reason why Mars doesn't have much atmosphere left.
We're talking about just solar flares.
Solar flares only smaller stars and bigger flares.
Yeah. Okay.
Closer up.
Right.
So probably Mars lost most of its atmosphere because of solar flares. If you were a little planet like Earth close to a small planet, the small stars that we call M stars, which are the most common, you would have lost your atmosphere a long time ago. So maybe atmospheres can be replenished. But anyway, so we're not going to be able to study a little Earth around an M star, small star, by this method. All we're going to see is that it's a rock. And so far, that's true. We've seen little rocks.
Okay.
So we need a different tool to see Earth around another star.
Right. Yeah.
I mean, Earth around another star like the sun.
Is that the HWO, you think?
Yes. Yes.
Okay.
Habitable Worlds Observatory.
Yes.
It's the chosen successor for the Webb telescope, according to the National Academy of Sciences committees that helps us decide what to do.
Sure.
Every 10 years, they write a book. They call it the Decadal Survey. And they have hundreds of people come together to write this book. And they say, this is the area of science that's really exciting. And these are scientific missions that could make big progress. So we don't have a design for this great new Habitable Worlds Observatory, but we know more or less what it has to be able to do.
Right. We know the end result, and we're going to build
It
backwards
needs
from
to be about as big as the Webb, at least.
Okay.
It needs to be quite well protected from those micrometeorites, otherwise it'll have bumps on the mirror. It needs to be extremely stable, because here's the problem that we have to solve. How are you going to keep the glare of the star from getting into where you wanted to see the planet? So if you want to study our solar system from a distance, you've got a sun that's 10 billion times as bright as the Earth. 10 billion. So that means you've got to get rid of basically everything except 1 part in 10 billion of the light of the star to see a planet. Okay, so that's hard. So you need perfect optics. And after you build them, you have to keep them perfectly focused and perfectly clean and perfectly aligned. And anyway, this is hard to do. Well, it's something we think we can do. It's called a coronagraph. Blocks the light, sort of the way that the moon blocks the light of the sun.
Right.
And we've got to see the corona of the sun that way. That's why it's named that way.
That's true. Yeah.
Yeah. So we could do it.
Okay.
But that's the job.
Hopeful. Yeah. So next I want to get into ORCAS and HOEE. But before that, let's maybe talk about kind of your thoughts on, as we look for life, the density of life. I mean, my thoughts are I've talked about this in other episodes, but it's pretty clear to me, just because of the vastness of space, the uniformity of the elements, and just the other variable of time. I can't imagine there's not a lot of Earths. Now we can talk about the level of life, but it must be that there's a lot going on throughout the universe. So I think you share that view.
I certainly think that too. It's not a proof. It's just a
Right.
guess.
Yeah.
But it seems to me that the forces that produced life here happened very quickly.
Yeah.
Within few hundred million years of evidence of an ocean, have evidence of life.
Yep.
So whatever it was quick.
Yeah, it's quick.
So that's evidence that it might happen elsewhere quickly also. That it might not be too strongly related to the specific details of what Earth is like. So on the other hand, we don't know. So what are we going to do? We get to go look. Go look at the other planets in the solar system, where if we find something, we could be really sure. I brought this rock home, and you know what? I put it in the petri dish, and it grows. That would be very great proof of life. It's still hard to prove it wasn't something you took with you.
Right.
But all the same, that would be very powerful.
Yep.
Or you see fossils that aren't alive anymore, but they sure look like they were. And they have chemistry to say it.
Yep.
Or you find water spritzing out from one of the ocean worlds outside. The satellites of Jupiter and Saturn have water, a lot of water. And we have already launched a probe to fly through the water plumes coming out of Europa.
Is that Dragonfly or is that Titan?
That's Europa Clipper. Is the name of Europa Clipper.
Oh, yes. Okay.
Yeah. So Dragonfly is the name of the helicopter that's going to fly around on Titan.
Yes. Okay. That's also exciting. So both can give us some cool stuff, possibly.
Yeah. So I don't know what they're going to find, but it'll be interesting. Either there is or isn't a sign of life on these objects.
Yeah.
But even if we don't see it this time, it doesn't mean it's not there.
Right.
But they're certainly different from home. Here,
certainly, yeah.
I think it's a pretty fair guess that Darwin was sort of right about where did life start. He said a little warm pond.
Yeah.
And I've been reading what other people say about this. And the story that I like is that you can have organic chemistry in a soup, but unless you do something to increase the constitution of the molecules, nothing much is going to happen.
Yeah.
But if you can say freeze dry or at least dry out or your little ponds so all the molecules condense onto the surface of something, then you have a chance to get something really interesting to happen. So nature seems to be set up so that if you get enough oily molecules in one place, then they will spontaneously form little cellular object, little round object with that may enclose some water inside. So spontaneous generation of little protocells seems to be a natural process.
Yeah.
Free biological. So,
right.
So this is one of those curious things that nature has set up this way.
Yeah, very curious.
And it's from our perspective, is a feature or an accident of organic chemistry that happens without biology.
Yeah.
So that's just what molecules do, and so they will form a cellular object given a chance.
Yeah.
But what is the chance that it takes? I think it needs a solid surface, or at least a place to concentrate molecules.
Yes. Hydrothermal vents has been a theory as well.
It's another one. It could maybe do it.
Yeah.
I think I like that idea too, because it's my analogy would be, suppose you want to try a trillion different science experiments. Each little place where the water flows through the tunnels in those vents.
Yep.
Different experiment.
Right.
Different molecules in different places, different chemical forces, electrical forces, energy sources. They're all different. So something could happen. I'm guessing.
Yeah. Here's a fun one. Do you think we'll know definitively maybe in my lifetime how it starts?
I think it's possible.
Okay. That's fun.
I think it's possible because I think there's enough progress being made that you won't be able to say, I know it happened this way, but you would be able to say, I know it could have happened this way.
Sure. Yeah.
Our ancestors ate the evidence.
Right. Yeah. That's true too. And I mean, the proving part is just the experiment itself is so tough because we're just on a planet full of life. So we need to almost do something not on Earth, which is, I mean, just such a hard experiment, such a hard experiment.
Yeah.
Um,
So we're not going to be able to easily say there's life on a planet around another star, but
Right.
what we have to do to find out. We have
right.
to build a telescope capable of seeing reflected light from a
Mhm.
planet the size of Earth around
Yeah.
a star like the sun, which is probably the best place to look. So we know what the requirements are on the observatory.
Yeah.
What are the molecules you want to find? Water, pretty likely.
Methane.
Oxygen is so active here that there wouldn't be any if it weren't for photosynthesis.
Right. Yeah.
So it's a result of an out of equilibrium process. Plant life is taking up sunshine and making oxygen in a cycle.
Mhm.
So if we find that, it's pretty strong evidence. You
Really?
have to prove that nothing else could have explained it.
Yeah.
But
If we did, so that's a good, because I counted out, because I don't know if it counts to me if we did, but if we did, would you, like, with the scientific community, they wouldn't make the claim, right? But they would say very strongly this is most likely life. But there's no claim to be made. It's a tricky one because we can't get down there. You know what I mean?
I think and when we get the World's Observatory and can see
Mhm.
that there's oxygen, a lot of oxygen in some planet, that would be something to argue about for quite a while. But I think it'd be hard for people to dodge the idea of life.
Okay. Yeah.
Because we haven't thought of any non-biological cycle that would produce that much oxygen.
Let's jump into hybrid observatories now, and this kind of new approach to using the best of both worlds, skipping all the dust and stuff in the atmosphere, getting up there, but also the largeness of a telescope down here, saving money. So that's what you have for ideas.
Yeah. So I started off my thought process with adaptive optics.
Mhm.
Adaptive optics corrects for the turbulence of the Earth's atmosphere.
Yeah.
And basically, it has started development at Berkeley when I was a grad student out there. A friend of mine named Rich Muller was working on it, and he showed me his lab apparatus when I was a student. Pretty soon after that, it was classified because of enormous military effect of the ability to see sharp images through turbulent air. So the military side and the secret side of things developed for decades. Until finally a French team developed the same idea, and you couldn't classify that anymore. So
okay,
how does this work? Well, you have to basically say that what should be a plane wave arriving from a distant source is no longer flat. It's been adjusted by passing through turbulent air. But if you could make compensating ripples by reflecting this incoming distorted wave off a distorted mirror, you could compensate for it all. And so that's the secret of adaptive optics.
Wow.
It's what they call the rubber mirror a long time ago, and so now you just need to have a way to figure out how to move the mirror, so that makes it adapt to the thing you're looking at. So if you're looking at a star, a bright star, you say, "Oh, I just sharpen up the image of the star."
Yeah,
and we know how to do that in principle. We measure the shape of the wavefront. We say, "Oh, just adjust it until it's flat," and get a sharp image. So that's adaptive optics. And however, the promise was not fulfilled for a long time for astronomy, because you could only do this looking at a bright star. And the bright star has a lot of glare around it. And the bright star is not where you wanted to look. You wanted to look somewhere else.
right.
So after a long time, somebody said, well, how about aiming a laser up into the upper atmosphere, tuned to the wavelength where sodium atoms will fluoresce. So shine laser up into the upper atmosphere, make your own artificial star way up there, and use that.
Oh, okay. So we're making sodium atoms excite to the point of light, and then
Yeah,
we're using that light to
you
come
can
back to us, and then
you
giving
make
us
a bright spot in the upper atmosphere
right.
using your laser.
Yeah. Okay.
Then you have something to focus on.
And then we get a differential to go off of, and we cancel it out, and then we have
Yeah, so it's enough to work. It's pretty hard to do, but they made it work.
oh
So this is adaptive optics.
yeah.
It's fantastically powerful. And it makes the telescope on the ground have as sharp an image as it would have if it were in outer space. Fantastic, especially when the telescope gets really big.
Right. Exactly.
So we've got the 10-meter class telescopes on Hawaii, the Keck telescopes.
Yep.
8-meter telescopes in Chile. And they're building a 39-meter diameter telescope in Chile. The European Southern Observatory is building the extremely large telescope.
Yeah, I love the name. It's a great
Yeah.
name.
And there are two US-led teams that are trying to build them too. Neither of them has enough money to get finished, but there's a giant Magellan telescope, a 30-meter telescope. So we could end up with 3 of these wonderful giant telescopes.
Yeah.
And you can just imagine how much more powerful they will be when they all have adaptive optics.
Right. Yeah.
Now comes a new problem. It doesn't work well enough, even all this fancy stuff with the lasers, at visible wavelengths, the kinds that you and I can see. It's just too hard. It doesn't work well. So what else could you do? How about making your artificial star that you focus on a satellite that you can put where you want it?
Yeah.
So that was our idea. And that's the orbiting configurable artificial star, the ORCAS.
ORCAS. Yeah.
So put your own guide star where you want it and let it hover there for several hours.
Yeah. And by the way, small sat, so much easier budget wise, right?
We could buy the parts today, and I don't have enough money in my checking account, but at least it's a small object. It's a person-sized satellite, not a giant observatory in space.
Right.
So, and it could work with any telescope.
Yeah.
So, and it's a whole lot simpler if you can make it go. It's a whole lot simpler than the ones with all the sodium lasers. So anyway, so that's a very exciting idea for me, and to see the possibility for this huge telescope to be effectively perfect.
Yeah. Effectively perfect. Would we send just one up, or would we send like a bunch up so there's bandwidth for everybody to use it?
Well, I think as many as you can afford after we prove that it works.
Yeah.
I think everybody will want one.
Yeah, I agree. Yeah.
Also, there is one feature which is not so wonderful, which is you have to put it in the right orbit. And so when you put it in the orbit to match up with a particular target star, it's not in the right orbit to do it for some other target. So you have to change the orbit to look at another target. So this takes energy, it takes fuel, and it's not instant. So you can't say, oh, I just want to look over there today. You have to plan ahead and have enough fuel. So eventually the thing will be out of fuel.
Right. Right.
So you launch another one.
Yeah. It's a trade-off, but I still think cheaper and easier than a whole thing in space. Yeah, definitely.
Yeah, it's certainly cheaper than building a telescope in space. And my thought is, well, if we prove that it works as well as I hope, then everybody will want one. And it'll be cheaper also.
Yeah, super exciting.
We already know what the part list is. We could buy all the parts.
Right.
So I think that's cool.
What do we have a timeline for when the first one's going up, or still waiting?
There's no proposal currently being submitted to NASA or anyone. But if we did, and somebody said, here's the money, I think you could have it in 5 years.
Yeah. Okay.
So a small object, and people in the industry can do that.
Yeah. Now let's get into a little further out, which the HOEE. That's a fun one too.
The HOEE, the Hybrid Observatory for Earth-like Exoplanets. So we already talked about how hard it is to do it with the Habitable Worlds Observatory, because you need a perfect telescope in space. So our idea was, well, what if you block the starlight with a shade, a very distant shade, and it's called a starshade. So it turns out it has to be extremely far away, and extremely large.
Right.
So the distance is set by the orbit at minimum. The orbit we need for the guide star story or for this one is at least 170,000 kilometers high.
Oh my gosh.
So otherwise, the thing will hit the Earth when it comes in close to the perigee. So pretty far, and it also tells you how big the shade has to be. In this case, about 100 meters across.
Really?
As big as 2 football fields side by side.
Yeah.
So bigger than my backyard. And it would cover a lot of the Yankee Stadium.
Yeah. And it would unfurl as well, and it would be a very thin material, I'm assuming.
Yeah. So we've got a design we're working on now, which would unfold by being inflated. So,
How do you inflate something in space?
Yeah. So yeah, you can inflate something in space.
Interesting.
You just make sure it doesn't have too many holes in it, and puff it up. So then you probably want to rigidize it after it's there, because the gas will eventually leak out because of micrometeorite holes. Anyway, there's things to do.
Okay. Yeah, and that's another thing. The micrometeorites with the larger you make something, the more they're going to hit. So
there's no question you'll get hit by them.
So
there's a lot of them. Yeah. But mostly they're tiny.
Yeah. Mostly
and there are ways to protect yourself.
Yeah.
Anyway, so this is the idea. A star shade, it looks like a pointy sunflower. And the math for it was worked out decades ago.
Okay.
And more than once, actually. But the NIAC, which is the NASA Institute of Advanced Concepts headquarters, supported it. A guy named Webster Cash at the University of Colorado solved this problem. And then more people have piled on and have somewhat better solutions, but he was the pioneer. And so we know it can be done. We know the shape that we have to have. And but the problem is that it's just huge.
Yeah. Yeah. NIAC also is the one who helped, I don't know if you know Slava Turistchev, who's working on the gravitational lensing.
I do, yeah.
Yeah.
For when we look at the gravitational lensing from 1,000 AU away, that one.
Yes, exactly. Yeah, we put it in the right spot, and we can use the actual stars as So when do we think that one's a little farther out, right? So you would maybe
So we are currently being supported by NIAC to do a study on that one. We will be writing a report in March and submitting a proposal for the next step around the same time.
Gotcha.
So there's a lot more work to be done. We're trying to build up our team. And our manuscript on this topic has just been accepted by Nature Astronomy. So we'll be published in March. And
I'll keep a lookout for that. Yeah.
They're going to put an image of our story on the front cover, although there isn't really a front cover in front publishing, but yet all the same, it's pretty cool.
Yeah. Yep. So you say those two are taking up most of your time nowadays, ORCAS and HOEE.
Yeah. Well, I'm split in many different directions, but yes.
Yeah, we need to clone you and use you for like 4 different things.
Yeah. So if it weren't for people like Eileen and my colleagues, I would never do anything, because it takes so many people to do what looks to the rest of the world as that was easy. It took a lot of people, every one of them.
Yeah. Yep. There's a machine behind you. Cool. Anything else you're working on besides those, or just?
Well, those are 2 examples of what we call hybrid observatories, but there's an even smaller one that's already in process. We're working on the design details as we speak. It's called the Landolt. Landolt was a famous astronomer, and his specialty was figuring out how bright the stars really are, calibration. So we named the mission after him. The head of it is Peter Plavshin at George Mason University. And so we are flying a standard star, an object whose brightness is known by tests at the National Institute of Science and Standards and Technology, NIST. So here's your bright star. We know how bright it is. And so we've never had that in the past. So that will be flying in a few years, just a very few. It's an approved project already, and it's what they call a Pioneers class mission, which means the budget's quite small and the object is quite small. You can carry it.
Wow. Okay. A lot of cool stuff going on.
Yeah. So that's the smallest one that I know of. There's another ambitious one, which is the Black Hole Explorer. Should mention it too. It's being led from Harvard, and it's you've seen the pictures of the black holes with the glowing rings.
Yep.
You can do it better if you can have another antenna in space.
Okay.
So I need to have something a few meters in diameter, and pick up millimeter wave signals, and relay them back down to the ground without losing any information to be part of the network of telescopes they've already got.
Right.
So it needs a laser communications link to send that information back down. And so I think is a wonderfully clever idea. We worked on it for a while here at Goddard. And, I think it could be done and will be done sometime. I think it's pretty tricky, but it could be done. And the claim is that this is the only way you can actually measure the spin of a black hole.
Gotcha. Yeah.
Because it affects the way that space is being dragged around the black hole. So it affects the way those light rays are orbiting around the black hole before they get out to come to us. So the shape and brightness of those little rings you see can get a lot of data. We're looking at something that's just outside the event horizon. The photons almost can't get out, but they do.
Yeah, but they do. Yeah. It's interesting to think, like, what are we going to be doing in 100 years from now?
Something pretty exciting.
Yeah.
I think because we're now at the point where if you can imagine it, you can build it. And in 100 years of manufacturing technology, in 100 years, a robot can build it for you. So
yes. Yeah, I've thought a lot about that, especially in space, like robotics in space, getting mined material off of XYZ asteroid, whatever.
Yeah.
And it's probably the future. It's just we're telling there might not even be need for humans to even go up there anymore.
Yeah. We certainly are getting better at robotics and robotic construction.
Yeah.
My version of let's go to Mars is let's send a robot to Mars and build me a house. And robot, when you've got the house built and the light comes on and there's air and water and the stove is working, then I'm going.
Yeah. Would you go to Mars? Would you go to Mars?
No, I wouldn't really, because
I wouldn't either.
You get sick on the way.
You get sick on the way. Yeah.
Lucky not to die on the way.
Right.
But if you could get there and hide underground to keep away the cosmic rays, then you would need then you'd need the robot to build you a house underground.
Wow. Yeah. That's a good point. Yeah.
So it's not impossible, and when and if our mega corporations can do that, maybe they will. If Elon Musk really wants to go, he's going to have to figure that part out too.
Yes, yeah, I think he wants to rebuild the atmosphere himself, which is I don't even know how that would
that's not happening.
We can't do that. Yeah, we have to go underneath. So
I've focused on terraforming Earth, so could we keep on living here, please?
Yeah, I think we should save Earth before we run around. I agree.
Yeah.
Yeah. Thanks, Dr. Mather. Thanks for coming.
It was fun talking with you, and there's so many more stories to tell, but that was a good dose for today.
Yeah. Cool. Appreciate it. Thanks for coming on.